In the last video, we saw that the curl of electric field was equal to 0, which implied that the electric field is a conservative field. Conservative field, or which indirectly says that the line integral is independent of the path. Therefore, line integral is path independent. Now, since we know that the line integral of electric field is path independent, we can define the electric potential which we represent by V. It will be a function of the position r. It will be equal to minus line integral of O to r E dot dl, where O will be some standard reference point. Usually we take O to be as infinity, and we say that the potential at infinity is equal to 0. Therefore, this is the definition of electric potential, which is negative line integral of the electric field from some standard reference point O to the point R, where R is the distance between the source charge and the point where we want to calculate the electric field. Notice that this definition of electric potential would not make any sense if the line integral of electric field depended on the path. That is, let's say, if we come from infinity to the point R along one path, let us call it path 1, and through some other path at the same point through path 2. Now, if the line integral of the electric field depended on the path, then the potential would not be a function of r, since its value will depend on the path we take. That is, if we come along path 1, it would have some value, and if we come along path 2, it would have some other value. Therefore, in order for this definition of potential to make sense, we need the line integral of electric field to be path independent, which it is. Therefore, the potential is a function of position r, and not the path. Now, let's say that we want to calculate the potential difference between 2 points in space. Let's say potential difference between 2 points A and B. So VB minus VA will be equal to, we know we can write VB as minus some reference point O to B E dot dl, and we can write minus of minus, which will just be plus. So we can just write plus integral of O to A E dot dl. Now we can write minus O to B E dot dl, and we can change the limit of the second integral. So we will have a minus sign in front, A to O E dot dl. Or we can write VB minus VA as minus integral. We can combine these two integrals now. So A to B E dot dl, that is VB minus VA. Now notice that in our final answer, we don't have the standard reference point O. Therefore, we can take any point as a standard reference point, since it is the potential difference between 2 points which has a physical significance and not the potential at a point. Therefore, we normally choose infinity as a standard reference point, as I said earlier. Now, another way we can write VB minus VA is by using the fundamental theorem of gradients, which says that as we go from A to B, we can write this as the gradient of the potential dot dl. This is the fundamental theorem of gradients. Now we can combine these two things. We see that the left hand side of the two equations is same, so we can equate these two equations. Therefore we can now write integral a to b gradient of the potential dot dl is equal to negative integral a to b a dot dl. Therefore, we know that these two integrals are equal. Therefore, their integrands must also be equal. So we can say that the electric field is equal to the negative gradient of the potential. So we see that the electric field is equal to the negative gradient of potential, where del is equal to dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap in standard Cartesian notation. One way to interpret this equation is that as we go along the electric field, the potential decreases, that is, the potential drops. And as we go against the electric field, the potential increases. Now let's say that we have some point charge q at the origin, and we want to find the electric field at some point P, which is at a distance r away from the origin where the charge q is located. Then the potential due to the charge q will be V of r will be equal to integral. We will take a standard reference point as infinity to the point r minus E dot dl. And we know that we can write the electric field as 1 divided by 4 pi epsilon naught, the magnitude of the charge, divided by r square r cap. So we can write this equation. We can take the constants outside. So it will be, we will take the charge q outside, 4 pi epsilon naught, integral infinity to r 1 divided by r square dr. Since we will make use of spherical polar coordinates, and the line element in spherical polar coordinates along r will be dr r cap, and E dot dl will be equal to this. We can write that as minus q divided by 4 pi epsilon naught, and the integral of 1 over r square will be minus 1 over r, and we integrate it from infinity to r, so which will be equal to q divided by 4 pi epsilon naught 1 over r. Now we can see why in the definition of the potential we have a minus sign. It is to bring out the potential of a positive point charge to be positive. If we had a negative charge, then a potential would have been negative, but since we had a positive charge, a potential due to a point charge at the origin is positive, which will be equal to q divided by 4 pi epsilon naught r. This is potential due to a point charge kept at the origin. Now, let's say we have n number of charges, charge q1, q2, like this up to n number of charges, and we want to find the electric potential at the point P, whose distance from the charge q1 would be r1, similarly from charge qn would be rn. Now, since the electric field obeys the superposition principle, then therefore the potential also obeys the superposition principle. Therefore, the net potential at the point P will be equal to the potential due to charge 1 alone plus the potential due to charge 2 alone, similarly till potential due to charge qn alone, which we can write as, we can take the constant outside 1 divided by 4 pi epsilon naught. Now this will be q1 divided by r1 plus q2 divided by r2 up to qn divided by rn. we can write the same thing using the sigma or summation notation. Summation as I goes from 1 to n, q of I divided by Ri. This is the potential due to n number of discrete point charges. Now, if we had a continuous source of charge, let's say the source charges were distributed in a volume like this, and we wanted to find the electric field at some point R, we could do the same thing. We will first take a small cube of area d tau and let the distance of this cube from the point P be R. Then the potential will be equal to, constants will come out, integral of, let rho be the volume charge density times d tau, where d tau is this small cubical volume, and we will integrate this over the entire volume. Let's write here volume to know that we will integrate over the entire volume, and this whole divided by R. So the potential due to a continuous source of charges would be 1 over 4 pi epsilon naught integral of rho d tau over R, and we integrate this over the entire volume. Here rho is volume charge density, and d tau will be some small volume element. Now similarly, if the source charges were distributed in a surface, we could have used sigma for surface charge density, or if it was continuous line distribution, then we could have used lambda for linear charge density.